Welcome, students, to today's comprehensive lesson on one of the most fascinating phenomena in physics, the Doppler effect. I'm excited to take you through this complete exploration that will help you understand not just what it is, but how it works and why it's so important in our modern world. Let's begin our journey into the world of waves and relative motion. Let's start with the fundamental definition. The Doppler effect is the change in frequency of a wave for an observer moving relative to the source of the wave. Now, this might sound complex, but let me break it down for you. Imagine you're standing on a street corner and an ambulance approaches you with its siren blaring. You'll notice three key points. First, the frequency increases when the source and observer approach each other. You hear a higher pitch. Second, the frequency decreases when the source and observer move away from each other. You hear a lower pitch. And third, this principle applies to all types of waves: sound waves, light waves, radio waves, and more. This is fundamental physics that governs everything from medical ultrasound to astronomical observations. Before we dive into the mathematics, let's appreciate the brilliant mind behind this discovery. The Doppler effect is named after Christian Doppler, an Austrian physicist and mathematician who lived from 1803 to 1853. Doppler first proposed this effect in 1842, and here's what's remarkable. He originally applied his theory to explain the colors of light from stars. He hypothesized that the color changes we observe in stellar light could be due to the relative motion between stars and Earth. This was revolutionary thinking for the 1840s. The effect was first experimentally tested with sound waves in 1845, just 3 years after Doppler's proposal. Today, this principle has become fundamental to modern physics and technology, forming the basis for radar systems, medical imaging, and even GPS navigation. Now, let's make this concept crystal clear with an example you've all experienced. Picture an ambulance with its siren on, driving down your street. Watch carefully as the ambulance approaches you. Notice how the waves line thought are compressed. They're bunched together. This compression creates a higher frequency, which your ears interpret as a higher pitch. You hear that characteristic "nee-na" sound getting higher and more intense. Now observe what happens as the ambulance passes you and moves away. The sound waves are now stretched out. They're farther apart. This stretching creates a lower frequency, resulting in a lower pitch. The siren sound becomes deeper and fainter. This change in pitch from high to low as the ambulance passes you is the Doppler effect in action. You've been experiencing physics in your daily life without even realizing it. Now, let's dive into the mathematical analysis. We'll examine 4 distinct cases, starting with case 1, source moving towards a stationary observer. Look at our diagram. We have a red source moving with velocity vs towards a green stationary observer. The blue lines represent wavefronts moving through space. Here's the key insight. When the source moves towards the observer, it's literally chasing its own waves. Each successive wave is emitted from a position closer to the observer, effectively compressing the wavelength. Let me walk you through the derivation step by step. We start with f0 as our original frequency, v as the wave speed in the medium, and vs as the source speed. The original wavelength is lambda equals v divided by f0. Now, here's the crucial part. The compressed wavelength becomes lambda prime equals v minus vs, all divided by f0. Why? Because in one period, the source moves a distance vs towards the observer, reducing the effective wavelength. Therefore, the observed frequency becomes f prime equals v over lambda prime, which gives us f0 times v divided by v minus vs. This is our formula for case 1. F prime equals f0 times v over v minus vs. Notice that since vs is positive and in the denominator, the observed frequency is higher than the original frequency. Case 2 presents the opposite scenario, source moving away from a stationary observer. Observe our diagram now. The source is moving away from the observer, and notice how the wave fronts are more spread out, represented by the purple lines. When the source moves away, it's running away from its own waves. Each successive wave is emitted from a position farther from the observer, effectively stretching the wavelength. Let me walk you through the derivation. We start with the same initial conditions. f0 is the original frequency, v is the wave speed in the medium, and now vs represents the source speed moving away. The stretched wavelength becomes lambda prime equals v plus vs divided by f0. The plus sign appears because the source is now moving away, increasing the effective distance between wavefronts. The observed frequency becomes f prime equals f0 times v divided by v plus vs. This is our formula for case 2. Notice that vs is now added in the denominator, making the denominator larger, and thus the observed frequency lower than the original frequency. This explains why the ambulance's siren sounds lower in pitch as it moves away from you. Case 3 introduces a different dynamic, observer moving towards a stationary source. In our diagram, the green observer is now moving with velocity VO towards the red stationary source. This situation requires a different approach to our analysis. Here's the key insight. When the observer moves towards the source, the wavelength remains unchanged in space. However, the observer encounters the waves at a higher rate because they're moving into the wave pattern. Let me explain the physics. The original frequency is f0, the wave speed is v, and vo is the observer speed towards the source. The crucial concept here is relative wave speed. From the observer's perspective, the waves are approaching at a speed of v plus vo. Think of it like walking towards someone throwing balls at you. You encounter them more frequently. Since the wavelength lambda remains v divided by f0, but the relative wave speed is v plus vo, the observed frequency becomes f prime equals v plus vo divided by v. This is our formula for case 3. Notice that vo appears in the numerator, making the observed frequency higher than the original frequency. Our final case, observer moving away from a stationary source. Here, the observer is moving away from the stationary source with velocity VO. The wavefronts remain equally spaced in the medium, but the observer now encounters them at a reduced rate. The physics principle is similar to case 3, but reversed. The observer is moving away from the approaching waves, so the relative wave speed becomes v minus vo. It's like walking away from someone throwing balls at you. Following our derivation, original frequency f0, wave speed v, observer speed away, VO. Relative wave speed, V minus VO. Wavelength remains V divided by F0. Therefore, the observed frequency is F prime equals F0 times V minus VO divided by V. This is our formula for case 4. With VO in the numerator but subtracted, the observed frequency is lower than the original frequency. These 4 cases give us the complete mathematical framework for understanding the Doppler effect in all possible scenarios of relative motion. Now, students, let's explore how the Doppler effect impacts our modern world. This isn't just theoretical physics, it's technology you use every day. First, radar systems. Police radar guns use the Doppler effect to measure vehicle speeds. The radar sends out radio waves that bounce off moving cars. The frequency shift tells officers exactly how fast you're driving. Weather radar works similarly, detecting the motion of rain droplets and wind patterns to predict storms. Second, medical ultrasound. When doctors examine unborn babies or check blood flow, they're using Doppler ultrasound. The sound waves bounce off moving blood cells, and the frequency shift allows doctors to measure blood flow velocity and detect potential circulation problems. Third, astronomy. This is perhaps the most profound application. Astronomers use the Doppler effect to determine if stars and galaxies are moving towards us or away from us. The famous red shift of distant galaxies, where their light appears more red due to the Doppler effect, led to the discovery that our universe is expanding. And fourth, GPS technology. Your smartphone's GPS system must account for the Doppler effect between moving satellites in your receiver to provide accurate location data. Without this correction, your navigation would be off by several meters. Let's consolidate everything we've learned today with our general Doppler effect formula. F prime equals F0 times V plus or minus VO divided by V plus or minus Vs. Remember the sign convention. Use plus signs when the source and observer are approaching each other and minus signs when they're moving apart. Here are your key takeaways for your examinations and future studies. First, frequency increases when source and observer approach each other. This creates a higher pitch or shorter wavelength. Second, frequency decreases when source and observer move away from each other, resulting in lower pitch or longer wavelength. Third, this principle applies to all wave phenomena, whether it's sound waves in air, light waves in space, or radio waves in communication systems. And fourth, the Doppler effect is fundamental to modern technology, from the medical equipment in hospitals to the GPS in your pocket. Understanding the Doppler effect opens doors to comprehending advanced topics like relativity, cosmology, and modern physics applications. You now have the mathematical tools and conceptual understanding to analyze any Doppler effect scenario you might encounter in your examinations or